We've looked at the different kinds of antibodies, and now we're going to look at some of the technological improvements we can make using these antibodies. Okay? And in particular, we're looking at the importance of monoclonal antibodies. That is, you can make a collection, a pot full of antibodies with both the same isotype and the same idiotype. That is, they are all identical. They are identical because they come from a clone of B cells, that is, a single plasma cell, B lineage cell, that is producing the same antibody. So what you've got is a monoclonal, single clone lineage antibody, and they're all the same. Ooh, what a deal. We can use these to treat cancer cells. You will find that sometimes people will put on the Fc stems something like radioactivity or a poison, and you've got a recognition site for a particular cancer epitope. In particular, monoclonal antibodies are currently being used in many cancer therapies because, for example, the one that's Herceptin is used to tie up growth factor receptors, growth factors. And so the ability to make a specific recognition molecule is very helpful therapeutically. It's also helpful diagnostically. That is, we have many assays, ELISA assays, that use monoclonal antibodies in order to specifically identify substances, either whether or not they're there or how much of them there are. So this then is a good deal. How do we make it? Well, you might think to yourself, you know, if I have a B cell, that B cell is going to make, that plasma cell is going to make one kind of antibody, so all I need to do is isolate my B cell and put it in a test tube, and I have a money tree. The problem is that B cells usually only live a couple of weeks before they die. That is, a plasma cell can be isolated, it will crank out antibodies, but it dies before you have a chance to really put it to any good use. And so what we do in order to do this is try to find some way of making that B cell immortal. And we do that by essentially engineering it to become what we would call a hybridoma. That is, we are going to combine a B cell with essentially a B cancer cell, a myeloma cell, and we're looking for cells that have the property of being able to make antibodies to a specific antigen and to live forever. So that's what we're going to do. We'll say inject a mouse or a rabbit or something with a particular antigen, and we then isolate from that rabbit, mouse, whatever, a bunch of the plasma or plasma B cells. All right, now these guys are not going to live very long, so what I need to do is put them together with a myeloma cell and hope that they fuse. So what happens is you take, you know, a lineage of B cells, you put it together with a bunch of myeloma cells, you put in polyethylene glycol, and that tends to disrupt the plasma membranes, and these guys tend to fuse together. So what happens then is you may have, as it turns out, unfortunately, if I have a myeloma cell, there's no telling whether I'm going to get two myeloma cells fusing, which does me no good, two B cells fusing, which is something that's not going to do me any good either, or what I really want is a myeloma cell fusing with a B cell. And then, hopefully, I will have a cell that does what I want it to do. And it's kind of like having a party. Somebody's going to bring the beer, and somebody's going to bring the chips. So what I have in your outline, and I've sort of done a reduced form up here up in the board, is a table that tells you what each of these cells brings to the party. So here we have the plasma B cell. the plasma B cell is going to produce the desired antibody. That's the thing we're trying to make last forever. Okay? Now, myeloma cells, B cell cancer cells, can often produce antibodies or parts of antibodies. So I specifically want a myeloma cell that has been engineered to produce no antibody. Because when I'm done with this, I want my antibodies to come solely from the B cell. All right. Now, why would I'm doing this? I'm doing this to confer immortality on my B lineage. And so my B lineage usually can only divide for a matter of weeks. Cancer cells, sadly being cancer cells, will divide indefinitely. This is one of the few times that's a good thing. So what I want in this case is for my plasma cell to bring the beer, the antibody, and my myeloma cell to bring the chips, the immortality. And to do that, I have to basically get rid of anything that is not a fusion of a myeloma cell and a B cell. So in this case, if I have just B cells fusing or they don't fuse at all, this is going to die out on its own in a couple of weeks, so I really don't care. But I do care about getting rid of myeloma cells, because I put a lot of these things in, and they could divide, and they could overgrow my antibody-producing cell, even though they're not good for anything and they're not making me any antibodies. So I put these guys in a medium that's called HAT medium. H-A-T. And a HAT medium has in it a substance called aminopterin. And aminopterin is going to, we'll see, block the de novo pathway. All right? So these are rapidly dividing cells, and a rapidly dividing cell has to make DNA. And in fact, immune cells divide so rapidly that they have a couple mechanisms for making sure that they have the amount of nucleotides they need to make DNA. They can either make them from scratch, and that is the de novo pathway. So they can start this by scratch and make enough nucleotides to live. On the other hand, if you want something to divide rapidly, you want to give them stuff via something that's called the salvage pathway. So if you give them the makings of these nucleotides, they will pick them up, salvage them, and put them into DNA. And so that salvage pathway is supplied by, among other things, hypoxanthine and thymine. And that's how you can make your purines and your pyrimidines. And so I put these cells in a medium that gives them the stuff that they need to grow rapidly. What I do that makes this medium particularly interesting is I also put in something called aminopterin. And you have all of these things spelled out in your outline. Aminopterin is something that actually blocks this de novo pathway. So my aminopterin will prevent this pathway from going. And that means the only way that these cells have to grow is to salvage. Except that the myeloma can't salvage. So now the myeloma needs this de novo pathway. I've got it up on the shelf. I'm making these things. I'm selling them to people who are trying to make their own monoclonal antibodies. And so I can keep a myeloma cell alive by giving it the sort of starting materials it needs to make things de novo and enough energy. And it can make it to live on. All right? However, when I put these two cells together and I'm selecting for a hybrid cell, that's going to be actually a hybridoma. When I'm selecting for hybrid cells, I put this in a medium that blocks the de novo pathway, and therefore will also kill off eventually all of the myeloma cells that have not fused with the B cell. In this medium, however, salvage can still take place, and so the B cells can salvage, but of course they're going to die in a couple of weeks anyway. But the hybridoma now has also the ability to salvage that came in with the B cell. So that this cell here can now divide indefinitely, produce the right antibody, and will survive in this particular medium indefinitely, whereas the two sources of the cells cannot, so that this is now selected. As with any technical process, I've made this sound simpler than it really is, okay? Even when I can get this cell, sometimes they don't produce at a ridiculously good rate. I have to do various things to tweak them. If I have a mixture of cells, I have to make a clone from individual cells. That's how you get monoclonal antibodies. And, you know, I have to be careful and keep it alive. If I do that, however, I now have my money tree. I have a lineage of cells that will consistently, for an indefinite period of time, crank out nothing but the same antibody over and over and over again. I have to check to make sure it's not mutating or misbehaving in some way, but basically I have a source of antibodies. And we have gotten so good at this that there are whole companies devoted to making different kinds of antibodies and selling them. So that these days you don't even have to develop your own monoclonal antibodies in many cases. You can simply buy them off the shelf. What this has done is just really broken open a whole areas of research that involve specifically identifying proteins and then marking them and tracking them, and in some cases manipulating them, killing them, and stopping them. So the ability to make a monoclonal antibody is one of the most remarkable and important usages that you get from the immune system. The ones that are used therapeutically often have 5 or 6 syllable names that are totally unpronounceable, ending in AB. And so if you have a relative or somebody that's being treated for cancer, they may be treated for something that's a monoclonal antibody. I've just recently found somebody who's being treated for pancreatic cancer with one of these things. Used to be a basically untreatable cancer. She looks great. And so I would like to close this antibody lecture with a reminder that these are not only entities that protect you personally when you yourself make them, but they are entities that we are learning to manipulate in order to protect us from environmental dangers and our own specific problems with diseases of all kinds.